Hello everybody, my name is Ethan. Welcome back to the channel where today we are hopping back into our machine learning course on Codecademy. In the previous video, we went through the start of a new section. So in the previous bunch of episodes, we finished a lot of this machine learning fundamentals with all of this stuff, specifically this supervised learning with all those chapters there. And now we're going into feature selection methods, which in the previous episode, or video I should say, we did the introduction and filter methods. There were two types of main methods, filter methods and wrapper methods. And then there was also one more, but we'll see if they end up going through that a little bit more in depth. Seemed a little bit less important, but we're going to be finishing up wrapper methods today. We got through about half of the wrapper methods after we finished filter methods. And so we're going to start off with sequential backward selection with MLX10. Again, in the previous episode, we did the start of wrapper methods, which included sequential forward selection. So we're going to go right into the backward selection. So if you missed any of it, please be sure to leave a view on the previous episode. I don't know. Can you leave a view? I guess maybe. I don't know. We're going to just hop right in, though, with sequential backward selection. It's another wrapper method for feature selection. It's very similar to sequential forward selection, but there's one key difference. Instead of starting with no features and adding one feature at a time, sequential backward selection starts with all of the available features and removes one at a time. Let's say again that we want to find three of the following, or we want to use three of the following five features: age, height, weight, blood pressure, and resting heart rate. Sequential backward selection will start by training whatever machine learning model you're using on 5 different feature subsets, one for each possible feature removal. So we start here, then here, then here, then here, then here. We go through all of them, and we'll see which one is the best. Let's say out of the 5 subsets, the model performed best on the subset without blood pressure. Then the algorithm will proceed with the feature set age, height, weight, resting heart rate, and then tries to remove each of the age, height, weight, and resting heart rate. So then it'll go and it'll take one more off until it's at 3. Let's say of those 4 subsets, the model predicted the best without weight. Then it will arrive at the subset age, height, and resting heart rate. The algorithm will stop there since it's arrived at the desired number of features. To implement the sequential backward selection in MLX10, you can use the same SFS class that you used for sequential forward selection. The only difference is that you have to set the parameter forward to false. So the object SBS is currently set to the sequential forward selection. Change the forward parameter so it uses sequential backward instead of forward. So again, we can just come in here and type false instead of true. So it's a backward. And we're going to use the fit to fit it. So we do sbf.fit, and then we'll use x and y. Very nice. Evaluating the results of a sequential backward selection. As you learned in the previous exercise, model.subsets is a dictionary that contains information about feature subsets from each step of an SFS selection model. This works with sequential backward selection, just like it did for sequential forward selection. So we just do printing the subsets, and then we'll get this interesting dictionary that's printed out. We can also use plot SFS .get metric dict to visualize the results of the sequential backward selection. So we do that, and we'll end up seeing that as the number of features grows, we get a little bit more information, which is obviously that's what we expect to see, right? In this case, though, it's not that much of a difference between 3 and 4 and 5 and 6. So it wants me to use subsets attribute to print a tuple that contains the names of features chosen in the previous exercise. Remember that we chose 3 features. Did you get the same feature set as you did with sequential forward selection? So it wants me to print out the name. And to do that, we'll do 3. So we would do SBS. So first, I guess, print SBS dot subsets, and then do we index it at it's already at 3, so if we index it at feature names. Does that work? Looks like feature aims is not what we want to print out there. Because we have a nice dictionary here, right? So first, you have the number 6. Perhaps if we do, and actually do add in that 3. Yeah, there we go. Nice. The reason I did that, obviously it's a dictionary here, but it's a dictionary within a dictionary, it looks like. So we have, 6, and then 6 is related to this dictionary, right? And then we have 5, and of course we had 3 features, right, as the same as last one. So now let's use the subsets attribute of SBS to print the accuracy of the model after doing backward selection. Recall that the original model was about 80% accurate when we used all 9 features. How does the accuracy of the model use with only 3 features? So we can do kind of something similar. So we do the print statement here with sbs.subsets underscore at the index of 3, right? And then we're going to do a separate index here to find the average score. And it looks like it's in something like that is called that. Right here is where I'm seeing it, average score. Perfect. We ended up seeing that it was about 74% accurate. Now we're going to use plot S. I don't know why I keep saying FCFs. I don't know what I'm saying, to be honest. SFS to print SBS dot get metric dict. And then I have to include the pt.2, which I didn't do. So, as you can see, when we dropped that 3 features, we actually see quite a sharp drop in the accuracy or performance of our model. If we would have kept 6 of those features, we would have seen an 80% performance or accuracy compared to what we got with the 74% accuracy. So that's quite important. Sequential forward and backward floating selection. Sequential forward floating selection is a variation of sequential forward selection. It starts with 0 features and adds one feature at a time, just like sequential forward selection. But after each addition, it checks to see if we can improve performance by removing a feature. If performance can't be improved, the floating algorithm will continue to the next step and add another feature. If performance can be improved, the algorithm will make that removal that improves the performance the most, unless removal of that feature would lead to an infinite loop of adding and removing the same feature over and over and over. For example, let's say that the algorithm just added weight to the feature set age and resting heart rate. The resulting set is age, weight, resting heart rate. The floating algorithm will test whether it can improve by removing age or resting heart rate. If the removal of age improves performance, then the algorithm will proceed with the set weight, resting heart rate. Sequential backward floating selection works similarly, starting with all available features. It removes one feature at a time, and after each removal, it will check to see if any feature additions will improve performance. But it won't add any features that result in an infinite loop. Floating selection algorithms are sometimes preferable to their non-floating counterparts because they test the model on more possible feature subsets. They can detect a useful relationship between variables that plain sequential forward selection and backward selection might miss. Let's say that sequential backward floating selection is being done on the set age, height, weight, blood pressure, resting heart rate. The algorithm removes weight, blood pressure, and resting heart rate in that order. After removing resting heart rate, the model had an accuracy of about 86%. Now it will try some feature additions. The possible feature additions give the following accuracies. Will it add a feature? Yes, I think it is going to add a feature here. To the name of the feature as a string. So it had an accuracy of 86%, and it's going to add weight. So we had a set of age, height, weight, blood pressure, resting heart rate. It removed weight, blood pressure, resting heart rate, meaning we were left with age and height. After removing resting heart rate, the model had an 86% accuracy. So now it's going to add back weight for a 95% accuracy, and I think that's what's going to happen here. We're going to add weight, and it's going to make it a lot more accurate. Sequential forward and backward floating selection with MLX10. We can implement sequential forward or backward floating selection in MLX10 by setting the parameter floating to true. The parameter forward determines whether MLX10 uses a sequential forward floating selection or sequential backward floating selection. As usual, the dictionary model.subsets will contain useful information about the chosen features. Here's an implementation of sequential backward floating selection. So again, we have this SFS class. We put in our logistic regression model, right? We're going to say how many features we want, 5. Out of however many there actually are, how many variables there actually are. Then we'll specify, is it forward selection? In this case, no, it's backward selection, so forward is equal to false. And then we're saying its floating is equal to true, which means this is going to be a floating or a sequential forward floating selection. So we can use the subsets attribute to look at the feature names by doing this, just like we did with the non-floating sequential. And this outputs this. So let's use MLX10 to create and fit a sequential forward floating selection model called SFFS that chooses 3 features. So it wants me to create this this one right here. So features equal to 3. We're going to uncomment these lines that say forward. So we want a forward. So forward's equal to true. But in this case, floating is also going to be equal to true. We're going to say scoring is equal to accuracy and CV is equal to 0. So now we can run that model. And now we can do print SFFS dot the info command, which is subsets. And then we want to pass in the amount of features that we have, which is 5. And then it says it wants the names of the features, which is feature names. 3. That's why. 3. Right here. So it looks like it chose age, glucose, and insulin as the 3 most prominent features that do the best. Now we're going to do the same thing, but a backwards floating selection model. So of course we'll say forward is equal to false. And then floating is still going to be equal to true. Scoring is just equal to accuracy. CV is equal to 0. And we can run this now. So we're doing the same thing as we did with the forward selection, and it ends up having a little bit of a difference here, which is very interesting. First, it does believe age and glucose are the 2 most prominent variables in the data set. Both forward and backward floating point selections, floating selections think this, but forward thinks insulin, while backwards thinks resisted. All right, recursive feature elimination. Recursive feature elimination is another wrapper method for feature selection. It starts by training a model with all available features. It then ranks each feature according to an importance metric and removes the least important feature. This algorithm then trains the model on the similar feature set, rank those features, and removes the least important one. This process stops when the desired number of features is reached. In regression problems, features are ranked by the size of absolute value of their coefficients. For example, let's say that we trained a regression model with the 5 features and got the following. The regression coefficient for age has the smallest absolute value, so it's ranked least important by recursive feature elimination. It will be removed. And then the remaining 4 features will be re-ranked after the model is trained without age. It's important to note that you may need to standardize data before doing recursive feature elimination. In regression problems in particular, it's necessary to standardize data so that a scale of features doesn't affect the size of the coefficients. Note that recursive feature elimination is different from sequential backward selection. Sequential backward selection removes features by training a model on a collection of subsets, one for each possible feature removal, and greedily proceeding with whatever subset performs best. Recursive feature elimination, on the other hand, only trains a model on one feature subset before deciding which feature to remove next. This is one advantage of recursive feature elimination. Since it only needs to train and test a model on one feature subset per feature removal, it can be much faster than sequential selection methods that we've covered. Say you want to choose 4 of 6 possible features for a model. If you use recursive feature elimination, how many different feature subsets will you test on a model? Set this variable to an equal to RFE underscore test underscore count. So it's looking for an integer. How many different feature subsets will you test on? Well, when we have 6, it's going to test that one subset, right? Then it's going to get rid of the last one. And we're going to have 5, so then it's going to test 2. So I'd say it's going to test 2. I think it's either 2 or 3. Yeah, 2. If you use a sequential backward selection to choose 4 of the 6 features, so if we did instead sbs.test, I feel a lot like it'll be a lot. 10 maybe. I don't know the actual number off the top of my head. Maybe I should, but it would start at 6. It would remove that feature, and then it would test every single one of the features. So it would test 1, and then it would test 5, so 6, so maybe 12. Let's see what the actual solution is. What is the solution? 11. I literally put 10 and 12, but it's going to take 11. So obviously, RFE test count is a lot lower. Recursive feature elimination with scikit-learn. We can use scikit-learn to implement recursive feature elimination. Since we're using a logistic regression model, it's important to standardize data before we proceed. We can standardize features using scikit-learn's standard scaler. From sklearn.preprocessing, import standard scaler, and we fit transform it using X. Once the data is standardized, you can train the model and do recursive feature elimination using RFE from scikit-learn. As before with sequential feature selection methods, you have to specify a scikit-learn model for the estimator parameter, in this case LR for our logistic regression model. N features to select is self-explanatory. Set it equal to the number of features you want to select. So we have recursive feature elimination. We import it from feature selection in the sklearn library, and we fit it to our data. So we're going to standardize our data by using the standard scaler. And then we're going to use sklearn to create this RFE object. We're going to call it RFE, set equal to RFE, and it's going to choose logistic regression, and then N features to select is the keyword, and we're going to set that equal to 2. Not 2, sorry, 3 features. Finally, we're going to use the RFE.fit method and fit it to our X variable and then our Y variable. Perfect. Evaluating the results of recursion feature elimination. You can inspect the results of recursive feature elimination by looking at the RFE.ranking and RFE.support. RFE.ranking is an array that contains the rank of each feature. Here are the features from FIRE dataset. Here are the features ranking after recursive elimination is done on the FIRE dataset. So it's saying that RAIN and FWI are just as important. A 1 is at a certain index indicates that recursive feature elimination kept this feature at the same index in this example. The model kept the features at indices 3 and 5, RAIN and FWI. The other numbers indicate at which a step feature was removed. 5 is the highest ranking. Okay, so 5 is the highest ranking in the data set. at index 1 means that RH, the feature at index 1, was removed. Okay. So 5 is worst then. I don't know why it says the highest rank in the array. Was removed first. The 4 means that it was feature was removed at index 2, was removed on the steps. Second step, RFE.support is an array with true and false values that indicates which features were chosen. I see. So we've chosen these two right here. We've chosen rain. We've chosen that to determine fire. Cool. The array indicates that features at indices 3 and 5 were chosen. The features at indices 0, 1, 2, and 4 were eliminated. If you have to choose a list of feature names, you can use list comprehension and RFE.support to get a list of the chosen feature names. Okay. You can use RFE.score to check the accuracy of the model. All right, we're going to create a list of features called RFE_features and set it equal to the names that of the features that were chosen by recursive feature elimination. So we can do that by doing this kind of interesting list comprehension here. So we'll do that, and we'll do the names. Okay, so the names is F for F support. We're just going to be copy and pasting almost this. I assume a lot of feature list, maybe. We'll print the accuracy of the model now. So it wants me to print the accuracy, which we can find in where? Where can we find the accuracy? Ah. %. Okay. Review. Congratulations, you learned a few different wrapper methods. You also learned how to implement them in Python and evaluate the results. Let's recap what we've covered. Wrapper methods for feature selection are algorithms that select features by evaluating the performance of a machine learning model on different subsets of features. Here are some advantages to wrapper methods. They detect relationships between features that might be relevant to the machine learning model. Unlike filter methods, they are designed to choose features that are relevant to whatever machine learning model you're using. We've covered 4 different greedy wrapper methods and implemented them using MLX10 in Python. That'd be sequential forward selection, backward selection, forward floating selection, and forward backward selection. We've also recovered recursive feature elimination, which ranks features by importance, and so on and so forth. We now have a bit of a test. Why are wrapper methods sometimes preferable to filter methods? Are more efficient. Features based on the performance. Yeah, that one right there. Select features. The importance metric. And removes every step. Which of the following statements about forwards false? That's true. That's true. Yeah, it doesn't start with all features. It starts with 0. Fill in the code. So to create an RFE object, say that you've used the scikit-learn library to implement a recursive feature elimination model called RFE. You also have the list of features. Here's the output. What set of features did the recursive selection choose? So it chose goals, points, and penalty minutes. false. It's the opposite. It is sometimes necessary to standardize data before using. This is true. Which of the following statements about sequential backward selection is false? True. Starts with all of them and then removes it one at a time. Yep. Remove the smallest regression coefficients. Test the performance of machine. Yeah. Fill in the code that will fit a logistic regression model. So we'll just do dot fit and prints its accuracy. Print score. Say that you've used the MLX10 library to implement a sequential forward selection model called SFS. Here's the output. Which of the statements is false? The accuracy of the model with the first two features is about 89. With two features, yep. GPA was the first feature. True. Wait. Cool. How many features does forward selection? 0. Fill in the code so that it will implement sequential backward selection. Models equal to SFS. Forward equal false. Floating equals false. Which of the following statements is true? Wrapper methods choose features based on evaluating the features directly. Independent, nope. Wrapper methods choose features by evaluating the performance of machine learning model on feature subsets. I like this one. Wrapper methods choose features by wrapping each feature in an array of numbers. Nope. Follow wrapper methods choose features automatically. I like that one the most, yeah. Which of the following statements is false? Logistic regression models predict the probability that observations belong to a specific class. That's true. Recursive feature elimination can be used to select features for logistic regression models. True. Sequential selection algorithms can be used to select features for true. Logistic regression model on. Cool. Did really well on that test. Pretty happy with that. I don't believe we have a project. Actually, we do. Never mind. So, we're going to just be doing wrapper methods, and it's automatically in Jupyter Notebook here, which is pretty interesting. We've never actually had a project that's automatically in Jupyter Notebook. So that's pretty cool. So in this project, you'll analyze data for a survey conducted by Fabio Mendoza. I'm just going to call him FMP. And okay, that asked people about their eating habits and weight. I just don't want to mispronounce it, that's all. The data was obtained from the UCI machine learning repository. Categorical variables were changed to numerical ones in order to facilitate analysis. First, you'll fit a logistic regression model to predict whether a survey respondents are obese based on their answers to the questions in the survey. After that, you use 3 different wrapper methods to select a smaller feature subset. You have 2 options. So let's start this up and see how it works. So the data in the obesity data set contains 18 predictor variables. Here's a brief description of them. The outcome variable, no obese is 1 if a patient is obese, 0 if not. Use the head method to inspect the data. So we do so here's the data. All right. I'm just gonna comment that out. Actually, it's not as important on this one because of how Jupyter.
Narrator dialog. Skip for now. Button. Exiting narrator.
Please tell me I'm not just cooked. How did it install narrator, bro? God damn it. That is so annoying. I really hope it doesn't. Okay. Hopefully it doesn't mess with anything. Sorry about that. Didn't mean for me to absolutely accidentally install the fucking narrator. That's annoying as hell, but we inspected the data. That's what we wanted to do. In order to use a logistic regression model, you need to split the data in two parts, the predictor variables and the outcome variable. Do this by splitting the data frame into predictors called X, a series, and outcome variables Y. So we're splitting the data. Basically, we can do this by saying X is equal to the data frame, which is obesity at the index of all the different features. So we can do this by just selecting all the different features here, which if we go up here, we can do just by copy and pasting all of them. Gender, age, family, history, with overweight, FAVC, FCVC, NCP, CAEC, smoke. Where did my cursor go? CH20. I assume that's a 0. SCC, FAF, TUE, CALC, so then we have the automobile, bike, motorbike, public, transportation, and then walking. And that's it. That should be all the variables there. After that, we can go down one to the Y variable, which is just obesity, the variable Nobia's dad. Yep. Next, we're going to create the logistic regression model called LR is equal to logistic regression with the max iteration equal to 1000. So it's saying that CH2, it was just an O. So that's very strange, but that's an easy fix, which is nice. Let's create the logistic regression model. We did that. We're going to fit the model using lr.fit to X and Y. We'll see how this goes. Looks like it ended up working, so that's nice. A model's accuracy is the proportion of classes that the model predicts correctly. It is compute and print the accuracy. I assume it's just saying compute and print the accuracy of LR by using the .score method. So if we do LR.score, passing in that X and Y, we'll see that we get a value of 76%. So our model is using all these variables. We're saying that our model is 76% accurate at identifying the obese trait. So sequential forward selection. Now that you've created, I assume we can now go. Now that we've created a logistic regression model and evaluated its performance, you're ready to do some feature selection. Create a sequential forward selection model called SFS. So we can do that by doing SFS is equal to SFS with the values of LR. And then we can do forward is equal to true. Floating is equal to false, because it's not a floating model. We'll then do scoring is equal to accuracy, and CV is equal to 0. We'll then, of course, also add in the K features is equal to 9. We're now going to fit this model by doing sfs.fit using x and y as parameters. Step will take some time. That's fine. We'll see how long it actually takes, because it's fitting this model. And we got it. Nice. What happens when we click that? I see. Cool. So now that we've run the sequential forward selection algorithm on the logistic regression model with x and y, you can see what features were chosen and check the model using the print subsets 9 to inspect the results. So we can inspect those results by saying print sfs.subsets at the index of 9, and we want to just select the feature names in this case, so we're going to add another little thing here that just says feature names, and we get them here. These were the biggest ones that incorporated it when we used the sequential forward selection. Perfect. Then use it to print the accuracy of the model. So we can do this again by doing another print statement. sfs.subsets at index 9. If we do this, we're going to find where we can find score. It's called average score is what it's going to be under. So then we can just highlight that by just saying average score. And now we get that score of 78%. So if we check, our original model ended up having an accuracy of 76.5%. When we did the sequential forward selection, it looks like the accuracy of our model increased to about 78%, which is obviously a percentage and a half, which is pretty good. We're excited about that. And now we can use the dictionary printed. Oh, is that not what I've done? Inspect the results. Okay. So we can move this down here and then just remove that. This will show us the index of all the different stuff, and then in the chosen features we can actually select and see this stuff. So we can now visualize it using plot sfs, sfs.get metric dict so now when we do that, we can actually end up seeing the accuracy. So it looks like we could have been all the way down at 64% accuracy with just one feature, but we're all the way up here at 78%, which is pretty good. We're happy about that. Okay, we're going to now do, instead of sequential backward or forward selection, we'll do the backward selection. So we're going to start it off by creating a backward selector called SBS, SFS keyword here though. And then we're going to pass in logistic regression. We want k features equal to 7. We want forward equaling false, floating equaling false as well. And then we want to do our normal scoring is equal to accuracy, and that CV is equal to 0. And I think that does everything there that we want it to. We'll fit the model using sbs.fit with x and y. This is going to probably take another minute or so for it to actually fit. So we can mark these ones down because that's exactly what we're doing. It's going to fit that model. It might take a second here just to fit it, but that is fine. We're okay with that. Yeah, it's taking just about as long as the last one, which is fine. Still in progress here. You can see it because it's the there's the star that's in there. Hopefully I'm doing this right. I think I am. We'll see what happens here. Because it's taking quite a long time. Hopefully everybody's having a good day today. Wow, it's taking quite a long time here. Just rewrite the code, rerun it, see what happens. Does have quite a lot of features to go through to get down to 7. So if you think about it, it's a lot more than the other one. With forward selection, you start at 0, right? And you could just go up to whatever number it is. So in this case, it was 9. So it went through a lot of different selections, but only had to go to 9. Whereas backward selection, it starts at 18 features and it goes down to 7. So we're actually doing 11 features that it's keeping. Or I guess no, it's just 7 features that it's keeping, but it's still going to take a long time. That's why I definitely think they lowered this one. We'll see what happens though. We'll probably not do anything to this video. I was just about to say I was going to edit it. I think you should just probably skip ahead until you see me up and working again. Again. Okay. So we're just creating the big three here, which is just the forward, backward. We didn't do any floating, which I'm a little annoyed about, but all right, if I were to edit this, I would do subsets dot subsets underscore 7 underscore, and then wrap. We're just inspecting, so I'm wrapping this in the print statement. Then we'll print the two. Print SBS dot. Oh, perfect. Ended up actually working. Nice. So it just took a little bit of time. That's fine. So now we can run subsets. If we run this one up here, we should see that we have all these right here, which is really nice. I think if we go into underscore, again using that 7 index, not 7D, 7, we can add the feature names. There are all the feature names. Then we do print sbs.subsets underscore at the index of 7 with the keyword average score. And we can see didn't do as well actually as the previous model. Actually did a little bit worse than just doing the actual model, which not exactly what you want to see, right? So now we can do a plot s50 sfs sbs.get metric dict, and we can see what ends up happening is pretty interesting. When we we start at 18 features, we're at about 76% accuracy, and we notice a little bit of a spike around some of these features, especially at 12. We see the biggest spike where we get up to about 76% accurate, but we don't ever go anywhere close to that 78% accurate that forward selection did see. Now we're going to try the recursive feature elimination. I've already checked them all off, but that's perfectly fine. It doesn't affect how I actually can do the steps. So before completing this task, you should uncomment all the code you wrote for the previous task groups. So it wants me to uncomment code. Was I supposed to comment code? Okay, so what I'm going to do actually is comment out the code. I think that's what it's trying to get me to do. So I will just comment out all these lines right here so that it doesn't have a chance of rerunning anything. Oops. Okay, cool. So we're going to do features is equal to x.columns. Before doing it, let's standardize the data. We're going to implement it by creating a standard scalar. Standardize x using fit transform standard. Did we end up setting what the standard scalar was yet? I don't think we did, but I could be wrong. I don't think so. So we're going to have to create the standard scalar object. Scalar is equal to standard scalar. do scalar dot fit transform x. Perfect. So now we can create it by doing the RFE object. Looks 8 features. Features, it's some weird keyword. Features to something select. N features to select. N features to select. Let's go to 8. Fit the model now. We can do that by just doing rfe.fit to x and y. This is going to take just a little bit, just like the previous one did. Oh, that one didn't take any time at all. But that's very nice, though. So we can inspect the chosen features. RFE, we did this interesting list regression that we did in the previous one, which was what? F for F support. Yeah, that's what this was. In what do we call the features list? Yeah, just features. And then we can print RFE features. Then we can use the score to do our print RFE.score with X and Y. 73.9%. Cool. Well, that's that project complete, which means that's going to be the end of this video. We are going to cover feature. Oh, well, let me think here. We have 1 minute on feature importance. Let's just do this. So feature importance, learn about the feature importance, how to calculate it. Introduction, when we fit a supervised machine learning model, we often want to understand which features are most associated with our outcome of interest. Features that are highly associated with that outcome are considered more important. In this article, we'll introduce you to the concept of feature importance through a discussion of tree-based feature importance, Gini impurity, implementation of scikit-learn, other methods. How long is this? Wow, quite long. We'll go through it. Why not? I don't know why it says 1 minute, because this, yeah, nobody's reading this in 1 minute. Feature importance in a machine learning workflow. There are many reasons why we'd be interested in calculating feature importance. Feature importance is often used in dimensionality reduction. We can also use it as a filter method to remove irrelevant features. Wrapper methods such as recursive feature elimination use feature importance, right? Feature importance may also be used in model inspection and communication. Calculating feature importance, there are many different ways to calculate feature importance for different kinds of machine learning models. We'll investigate one tree-based method, Gini impurity. Imagine for a moment that you're interested in building a model to screen candidates for a particular job. In order to build this model, you've collected some data about candidates who you've hired and rejected in the past, and certification status. Consider the 2 following decision trees that these features to predict whether the candidate was hired, right? So all applicants, we hired them. So if they had a greater than 5 years experience or less than 5 years experience, right? Certified versus not certified. Looks like we're only hiring certified ones and only rejecting non-certified ones, where it's a little bit more or less, you know, oops. Which of these features seems to be more important? Looks like certification is more important. All candidates with certifications were hired, and all candidates without them were rejected. Gini impurity is related to the extent to which observations are well separated. Observations on outcome are well separated based on the outcome variable at each node of the decision tree. For example, in the 2 trees above, Gini impurity is higher in the node with all candidates, whereas where there are an equal number of rejected and hired candidates. So we can do Gini importance here in scikit-learn to demonstrate we can estimate feature importance using Gini impurity. We use the breast cancer data set from sklearn. So we can do this. Next we'll do the decision tree classifier, right? We did decision trees in a previous video. So it's kind of just talking about why this is important, right? Why features, importance. Yeah, feature importance. Okay, perfect. In the next video, we are going to be going into unsupervised learning algorithms. So we ended up doing supervised learning algorithms for a lot of this, but unsupervised learning algorithms will be next. If you did enjoy this video, please be sure to leave it a like, subscribe, and I will see you in the next one. Thank you so much for watching. Peace out.